All right, hey, welcome back. Post midterm. A lot of people are taking a break, I guess. Any before I start with the material, any questions about the midterm that I can answer? Yeah. We won't go over it. In recitation, we won't go over it, but the solution for the open-ended one is posted. And for the multiple choice questions, I realize you don't have access to it on Gradescope. So I have extra long office hours on Friday. So come to my office and you can look at the questions when you're there. Also, if you have any questions about which problems you got wrong on multiple choice, come Friday to office hours. Other questions? Yeah. No, I can't post because I'll reuse we keep the questions to be reused in other semesters. That's why we're not releasing them. Other questions? All right, so let's do a little recap because I know it's been a while. So what is the stuff that we've been doing post midterm 1 material? So graphs. So remember we started graphs, just basic introduction, directed, undirected graphs. We talked about how they come up in real life. And what we're going to do, what we've been doing is looking at algorithms, common algorithms on graphs. We talk about different types of graphs, so sparse graph versus dense graph. That's something that is going to come up on this current homework. It's not explicitly stated, but there's a question related to sparse and dense graphs. We talk about different representations. So adjacency matrix and adjacency list were two ways to represent graphs. Then we started with algorithms. So we looked first at the reachability problem, which is given a vertex V, mark all the vertices that can be reached from V. And there was a very simple algorithm to do that, this explore algorithm. And we saw that explore, starting from a node, visits every other node in the connected component of that node. Right, so we showed that explore, in fact, solves this reachability problem. It also, and so the extension of explore was to depth first search. We extended explore so that everything is visited, not just the vertices in the same component as V. So to do that, we added this outer call, which just made sure that every vertex gets explored. So for all vertices, if it's not visited, we explore it. So it runs explore on something. When that explore is done, it's done with that connected component, we restart explore again from some other unvisited vertex until we visited everything. And that was DFS, depth first search. And we right away saw how it's useful, how it can be useful to find connected components in a graph. We also then looked at, besides just finding connected components, we looked at, we added to this depth first search labeling of start and end times, this pre and post visit time to every vertex. This was like here, we did an example, it marked the time that we were exploring this vertex. Together with that, we talked about this forest, this TFS forest that gets constructed, which reflects the order in which we explore vertices. And within that, from these numbers, right, and also from this forest, we came up with a classification of edges into 4 different types. There were tree edges, back edges, forward edge, and cross edge. And there were 2 ways we could define this classification. First, the definition that we started, which was in terms of this tree, or the forest, if it's more than one tree. In this forest, let's refresh the edges. The solid edges were edges along which we explored in the graph. And then the dotted edges were all the other leftover edges. When we talk about the forest, we're referring to just the solid edges. They form a forest. But if you look at the solid and the dotted edges, then this graph is just the same as this graph. It's just we're drawing a different. Now, how do I tell if an edge, for example, this one is a back edge, or what type of edge? We look at, we have 2 ways. One is we look at it in the forest. And in this case, it's an edge from a node to its ancestor. That is definition of a back edge. Okay. Or we can look at the intervals. So here's a back edge, and we see that the vertex, the vertex from which we begin the edge, its interval is contained in the interval of the vertex where we're going. And this is, we were showing here that the edge from U to V, the interval of U lies within the interval of V. That's another way, equivalent way to classify a back edge. And we had similar ways to classify a forward edge and a cross edge. A forward edge, in terms of the tree, was just like the back edge, except it went down. It went down from a node to its ancestor, sorry, to its descendant. And that was a definition of a forward edge. In terms of the interval, it was the opposite. So of a back edge. So U's interval contained V's interval, not the other way around. So here's U's interval contained V's interval. And then all the other edges, leftover edges, were called cross edges. So this was a cross edge. Notice that it's not going from a node to its descendant or to its ancestor. And it's also not in the tree. So this is a cross edge. In terms of the intervals, we have that V's interval is start and finish before U's interval. Now at this point, I want to add a new point that I didn't mention last time. You might be curious, what about this? What if U's interval is completely before V's interval? Right? This is the 4th case that's not listed in here. Like we have U contains V, V contains U, V is before U. We also have to ask about U before V. And U overlaps V, overlaps V, but not contained. We already saw that that's impossible. So all that's left is this, and this I wanted to say is also impossible. The reason is, well, what does this mean? This means that I started exploring U, I finished exploring U, and then I started exploring V. But if there's an edge from U to V, I couldn't have finished exploring U before I started exploring V. Maybe we can see here with an example, like let's say A to C. I start exploring A. Even if I go to B, remember I did this thing, went all around, and even if I do all that, I cannot finish exploring A until I start exploring C, right? So it's impossible for this final case is impossible. I mentioned earlier that one of the goals of these pre and this back edges and everything is to be able to determine if a graph has a cycle. And now we'll see how to do that. First definition, directed acyclic graph called a DAG is a directed graph i.e. we will write digraph as short for directed graph that does not have and the associated problem with this is given G is G DAG. It turns out DAGs are really a special kind of graph. A lot of problems, algorithmic questions become easier or faster to solve if you know in advance the graph is a DAG. If you know in advance, there's no cycle. We'll see, I think next lecture already, or 2 lectures next week maybe, how looking for shortest paths becomes much easier in a graph that's acyclic than in a graph that has a cycle. Also, DAGs are important when dependency graphs come up. So, for example, your prerequisite chain. Ooh. Halfway through the semester, still people are trying to log in. So you have, for example, your classes that you need to take, and 360 is a prerequisite for 465, and 465 is a prerequisite for 464. And remind me, 360 is a prerequisite for something else, probably 461. And you have some prerequisite probably from 360 and so on. So you have this dependency graph of your classes. Why is it important that this graph is a DAG? What happens if there is a cycle, like if I add an edge like this? What does it mean for your graduation? You can't graduate. Yeah, you can't graduate. So if there's a cycle in a dependency graph, you have a problem. You have nowhere to. You can't take 360 because you haven't taken 464. You can't take 464 because you haven't taken 465, and you can't take 465 because you haven't taken 464. So it's quite important for these graphs to be acyclic. Now, if in this kind of graph, you have like I don't know 20 classes or something, and you can look at it and determine easily if there's a cycle or not. You don't need an algorithm. But imagine you are scheduling jobs on a cluster, like you're the scheduler, the scheduling algorithm running on Amazon Oz cluster, and you get this chain of processes, so that give a dependency, have a dependency graph. So process A is needs to finish before you run process B, and process B needs to finish before you run process C. So if in this kind of graph, if you have a cycle, the scheduler will never run anything because it will never have the dependencies completed. So it's important for the scheduler to be able to detect cycles and maybe tell the user, or maybe break the cycle, maybe just like kill one of the jobs, whatever is appropriate in that situation. But the first step is to detect the cycle. Here's another example from your book. Right. This is an acyclic graph. Notice there's no cycle. For example, you might initially think this is a cycle, but remember, it's a directed graph, so you need to follow along the edges. In other words, you can't go from A to C and then go to D. The edge doesn't let you do that. All right. Any questions so far? All right. So I make the following claim about, and this is related to how to find a cycle, that a digraph G has a cycle if and only if G has a back edge. So here's a connection between, like this is going to lead to an algorithm for finding if the graph has a cycle or not, just by running DFS and checking if there's any back edge. Right, so this claim is true, which it is, we'll prove it in a second, then it gives us immediately an algorithm. And we'll go through the algorithm also after the proof of the claim. Okay, so for the proof, remember, if and only if, so we have basically two separate parts that we want to prove. Let's look at the first direction from right to left. Suppose G has a back edge. And let E, the edge E from U to V, be a back edge. Okay, because there may be many back edges, let's fix one. We need to show that G has a cycle. Well, to help understand this, let's look at an example here. In our example here, we have here a back edge. How do you, what's a cycle? Once you know that that's a back edge, what's the cycle? There's a cycle that contains it, right? This one. Same for this back edge. See this back edge? But that gives you a cycle as well. That's the intuition. Why? Well, the definition of a back edge is that you go from a node to an ancestor in the tree. But an ancestor in the tree means that there's a way then to come back down to the original node. So this DAC then can be mapped onto this graph as well. And that's the intuition there. Let's just, and pretty much that's the whole, there's really nothing more to that than just writing it down, that by definition of back edge, there exists a path from V to U, which we call P. So this is a new notation. I'll write out, we'll be using it later. So this means a path from V to U, which we will call P. Okay. So we've got a path. I'll draw it here. We have V. We have a path to U. And now we have our edge, E from U to V. There's an edge. This is edge E. This was path P. Okay, so there's our cycle, combining E with E gives a cycle. That's the end of that part of the proof. Let's look at the other direction now. This one is a bit more tricky. We have to show that if there is a cycle, then there is a back edge. If there is a cycle, there is a back edge. So let's suppose G has a cycle. Let's give it a name. Let V0, V1 dot VK, and then back to V0 be a cycle. Now we have to show that there is a back edge. Let me give you some intuition for that as well. Again, with this example. Imagine there's some cycle in this graph. How does this cycle look like in this different way of visualizing the graph? Like a forest plus these extra dotted edges. How can that cycle look like? Well, it's maybe going down the tree at some point. Like if it's using tree edges, then it's going down the tree. But if it's a cycle, it has to somehow come back up the tree. Right? It has to come back to the first node. And that place where it comes up to the first node, this is the back edge. So this, like the cycle, EFB, this cycle, EFB, right? So it's at some point we have to go back up the tree. Right. To formalize this, to formalize this argument, we have to identify this topmost node in our cycle. Right? That's because, like, right, the cycle might start from E to F to B, might go like this. So there's no back edge going to E. The back edge involves the very, very top node. So we have to find what that top node is. I mean, we don't have to actually, it's a proof, so we don't have to find anything. We just have to give it a name. Let VI be the node that was discovered first. The node, let me be specific, the node from the cycle that was discovered first. Was, let's say, the earliest to be discovered. In terms of the DFS, pre and post numbers, this is the number with, this is the node with the smallest free number, the smallest the start number of the interval. Right, it's the first one to be discovered. Okay, so going back to our motivation, now we've called this guy VI. Okay. Now we just need to identify what this edge is. This is going to be our back edge. Well, that's the edge from just the previous node on the cycle. That's the node. If this is VI, then this is VI minus 1, previous one. So let E be the VI minus 1 to VI edge. Okay. And now to show that it's a back edge, we need to remember the definition of a back edge. Back edge is an edge that's going from a, let's see it, it's going from U to V, where V is an ancestor of U. So the second node is an ancestor of U, and so here, observe that the second node VI is an ancestor of VI minus 1. In other words, well, I think that is the way to say it. So VI is an ancestor of VI minus 1. Why is this observation true? Well, when we're running DFS, the first node we hit on the cycle is VI by definition, by the way we defined VI. When we explore VI, remember we are going to explore the whole connected component before we're done with VI. In particular, that means that anything, if there's a path from VI to anything, we're going to explore that. And so VI is going to be an ancestor of whatever we explore. In this case, there's a path from let's say VI is here. There's a path to VI minus 1 because it's a cycle. Because there exists a path from VI to VI minus 1. Therefore, E is a back edge. And that's exactly what we needed to prove. Again, this proof, the second part is again just, it's a kind of formalization of the intuition of the picture. You take a cycle here, you identify the topmost node VI, you look at the edge from VI minus 1 to VI, then you just have to formally verify that B is an ancestor of F, okay, in the forest. Once you do that, that shows you that this is a backend. Questions? Yeah. How come VI minus 1 is? How come it's not what? Yeah, okay. So the question is, why is VI the ancestor of VI minus 1 and not the other way around? Because we picked VI to be the first node to be discovered, which means it's at the higher point in the tree than all the other nodes on the cycle. And all the other nodes on the cycle are below the tree. So there's some tree below, and here's VI minus 1, and this is the edge going back up. Other questions? Yeah. Pre, this one? Pre number. Right, so we can do this example here. Let me move this guy. Let's do a DFS on here. So we open A, we go to C. From C, we go to E. Then we're done at E, we go up to C, and then we go to F. So we open F at 5. We're done with F. We're done with C. And we're done with A. Then we start at B. We go to D. So this is 10, closing at 11, closing at 12. What are the remaining edges? We went from A to C, C to E, C to F. Then went from B to, we didn't do B to A, we did do B to D. So the dotted edges are the ones we didn't explore, which is from B to A and from D to C. Now this graph, we said earlier, doesn't have a cycle. So as a sanity check, we shouldn't have any back edges in here. Okay. And so all these, the solid edges are true edges, and these are cross edges. The dotted ones are cross edges because they're actually going between different different trees in here. But in general, they're not going to an ancestor or to a predecessor. This is just a sanity check of the theorem. And we'll come back to this example later today. Questions? Yeah. If we started from B, possibly. Yeah, so different orderings of the vertices will give you different trees. The only thing the theorem states is that because the original graph doesn't have a cycle, your forest is not going to have a back edge. So this is regardless of the ordering of the vertices that you have. But forward, backward edges, that may change depending on how you start. All right, this takes us to another closely related problem, linearization or topological sort. We'll tend to call it linearization in this class. But a lot of people elsewhere, like other books, use topological sort. So be aware of both. Be aware of both terms. They mean the same thing. So this is the problem. Given G, find an order on the vertices if one exists such that edges always go from earlier to later vertices. So like in the above graph, we could write A, let's just try the alphabetical if it will work. A, B, C, D, E, F. Let's see if this is a valid ordering. So to do that, we just draw the edges. Let's see, from A, we have an edge to C. From B, we have an edge to A and to D. We can keep on going, but we already found a violation of the ordering. We already have an edge going from right to left, from a later guy to an earlier guy. So let's try to fix it. Let's put B before A. So now we have from B to A and from B to D. From A, we have a thing to C. From C, we have to E and to F. From D, we have to C. All right, so we thought we have a problem. Another backward edge. This back, I try to not call it back edge because it's not the back edge from DFS. This is just a edge going from right to left. Okay, so let's maybe swap D and C. Let's maybe redo this, swapping D and C. We'll put D first and then C. All right, so from B to A, from B to D, from A to C, from D to C, from C to E, and from C to F. Okay, so this is valid ordering. Okay, so why is this problem important? It goes back to the same motivations that examples we saw before. So if you, for example, for the prerequisite chain of classes, what does a linearization correspond to in real life? It's an order for you to take the classes. So you can take the classes in that order, and then you're satisfying all the prerequisites. For if you're you have a dependency graph, for example, for a scheduler, then coming up with a valid ordering is an order in which you can run the processes so that all the outputs are ready for when they're used as inputs. Here's another example of a dependency graph. And it's more of a funny one than one that you would write an algorithm to solve. But this is from another textbook. This is the getting dressed in the morning dependency graph. And so you can You first have to put on your undershorts before your pants, and your pants before your belt, and your socks before your shoes. But notice, like, according to this, you can put your socks on after your belt. You can put the watch on at any time. This was all like funny and not related to reality until I had a baby. And then every morning with my toddler, we have to reinforce that there's the dependencies when she's getting dressed. So it has that real life application. But jokes aside, so a linear ordering here would be a way for you to get dressed in the morning to make sure you satisfy all the dependents. Okay, so that's the problem, that's the motivation for it. Now, how about an algorithm? It turns out this is very closely related to whether a graph has a cycle. Notice that here, there's no cycle, and there's no, and then there's a linearization. What if there was a cycle? So what if here there was an edge from, let's say C to B, then this particular ordering wouldn't be valid anymore because you'd have this edge going from right to left. But could there possibly be another ordering that's valid? No. Think about how this cycle, CBD, how it would look like. In some ordering, you give some ordering. Well, it's a cycle, so you might be going from left to right, but at some point, you'll have to revisit the original vertex again, the first vertex. So at some point, you'll have to go from right to left. That's the intuition. So that's the intuition for why, if you have a cycle, there's actually no way you can find an ordering. Intuitively also, like, think about a dependency graph. If you have a cycle in a dependency graph, then, like you guys said, you for example, prerequisite chain, you can't graduate. There's no valid ordering of classes that you can take so that your prereqs will be satisfied. Turns out the other direction is also true, meaning if you do not have a cycle, then you're guaranteed to have a linear ordering. Your dependency graph of classes doesn't have any cycle, then no matter how complicated it is, there's always an ordering of classes that you can take so that your prerequisites are satisfied. We're going to write that down, and we're going to prove it formally. We'll claim graph G can be linearized if and only if G is a DAG. So again, it's an if and only if statement. So we have two separate things to prove. Let's prove the easier direction first. Let's say G can be linearized. Suppose G has a linear ordering. Well, we need to formalize this idea that I was saying, that if you have some cycle like CBD, then no matter the ordering, you at some point will have to go back to the first vertex in that cycle. So we need to just in order to write this down formally, we need to basically find the edge that's going backward, give it formally explain what that edge is and explain that it's going from right to left. So we need this first vertex or whatever it is, the leftmost vertex on the cycle. So if I recycle, right, if in my example it's like this, I need to find what is that first vertex. So let's do that. We are going to, for the sake of contradiction, assume G has a cycle. And we'll call it, again, V0, V1, Vk, going back to V0. Let that be a cycle. And let Vi now be the leftmost vertex in that cycle. Be the vertex that is earliest. Ordering, right, at the very left. Okay, now the edge, then the edge going into that. So Vi minus 1 to Vi is from right to left, i.e. it violates ordering. That's a contradiction. Questions about this direction? How many of you are comfortable with the argument? Not I think more than half. So good time to ask any question. Where's the earliest point, for example, where it stops making sense? Ask about that. Yeah. Okay, how do we know there's an edge from Vi minus 1 to V? Because it's a cycle. So, so there's some Vi here, and there's some Vi minus 1 right before it. So just the for example, D, C, E. DCB in this top graph is a cycle. DCB going back to D is a cycle. So what the notation I'm using would say V0 equals to D, V1 equals to C, and V2 equals to B. And then I have like, so this was a cycle D to C, C to B. But when I'm making it more general, I'm writing V0 to V1 to V2 back here. Now, which of these DCB, which of these is the earliest, is the leftmost in the ordering? It's B. So 2, V2, right? B is our V2. So Vi equals to V2 equals to B in this example. Vi minus 1 to Vi is the edge from, so what is Vi minus 1? Let me write it. Vi minus 1, well, this is V1, right? Because I is 2. I minus 1 is 1. So V1 is equal to C. Then Vi minus 1, this edge that I'm talking about, is actually an edge from V1 to V2, which is equal to an edge from C to B. Now what I'm saying is the edge from C to B, actually this orange edge, is going from right to left. Thanks for the question. Other questions? How many of you are kind of comfortable with the argument? Still some hands not going up, so questions? Yeah. Um, so once you fix an order for whatever this order is, then there's only one that's going to be earliest. But yeah, if you look at all the possible orderings, then yeah, any one of these on the cycle could be first. So this guy could be, instead of BADC like that, we could have written B A C D. It could have been like that. And then the cycle would have been from, again, D to C, C to B, B to D. So in this case, the VI would have been this guy. It really just depends on the ordering. That's why we can't use this example to prove that. That's why we have to be more formal and say for any ordering, there's going to be some first guy. We're going to call it VI. Okay, so now we got to prove the other direction, and this is the little harder direction. So this other direction says that suppose that G is a DAG, so does not have, we're going to need to prove that it can be linearized. How do you, yeah. Does not have a cycle, thank you. Does not have a cycle. We need to then show that G can be linearized. What's the easiest way to show that G can be linearized is to give an algorithm that gives you an ordering, and then just prove that that ordering is valid. Valid, I mean no edges going from right to left. Okay, so let's do that. You won't be shocked to learn that we're going to run depth first search on G. And from this, we're going to construct the ordering. Follows, we're going to order vertices in decreasing order of their host number. Let's do an example. Let's take our example here. In this example, we're going to look at decreasing post numbers. So what's the highest post number in here? Post number, I'm referring to this second one. What's the highest post number in here? Yeah. 12, okay. And that corresponds to B. Okay. What's next lower after B? D. Right, D has 11. What's next? What has the next lowest number after D? A. Yeah, A has 8. And then C has 7. And then F has 6. And then finally E. All right, so that's the linear ordering that we're going to construct. And I'm going to claim that this gives a linear ordering. I would say valid ordering. Let's double check on this example. So if I now put all the edges, this BC I'm going to delete because it was not part of the original DFS. So from B, I go to A. From B, I go to D. From D, I go to C. From A, I go to C. From C, I go to F and to E. 3, 4, 5, 6. Okay. So this is, in this example, this is a linear ordering. All right. But let's prove why in general. For the proof, let's do a proof by contradiction. So for the sake of contradiction, assume there exists an edge from U to V such that U is later than V. The contradiction, an edge going from right to left. So from U to V, where U is later than V. What can we say about that? Given the way we constructed the ordering, by the construction of the order, in other words, in decreasing order of post, we should have that post U is less than post V. What type of edge is E? Now that we know something about its post numbers, what type of edge is E? Let's look at, by definition of edge types, E is something edge. So let's look at the definition. Post U less than post V. Let's use this definition here. Here I should say. So we have 3 possibilities. Where is post U less than post V? Here, this is the closing of U. It comes actually after closing of V. Here, the closing of U again comes after closing of V. And only here does close, like U close before V closes. So this has to be a back edge. This is a back E is a back edge. What do we know about a graph that has a back edge? Earlier claim, G has a cycle. And that contradicts that G. Remember, we started with that G does not have a cycle. So let me go through this argument again. We're trying to prove that if G does not have a cycle with a DAG, then it can be linearized. So to do that, we actually give an algorithm to create an ordering. The algorithm runs DFS on G, and then looks at the post numbers and orders vertices in decreasing order of post numbers. Okay. And now if I want to show then this is a valid ordering. And if it is, then we're done. We've showed starting with G as a DAG, we've given an algorithm, given ordering, and if we can show that it's in fact a valid ordering, then we're done. We've shown that G can be linear. So that's where we boil down to this claim that that ordering is valid. Remember, so far, we haven't used anything about the fact that G doesn't have a cycle, right? We just ran a DFS, created an ordering. Okay. But now to prove that this ordering is valid, we are going to rely on the fact that G does not have a cycle. The way now we're going to do this is a proof by contradiction. And we're going to say, well, what if G, let's assume for the sake of contradiction that G is not a valid, sorry, that the ordering we created is not valid. In other words, there's some edge that's going from right to left. U to V, where U is later than V. Turns out that that edge has to be a back edge. Why? Well, the way we constructed the ordering, if U is later than V, then its post number is smaller. Now that tells us the category of the edge. We look at the definition of the categories of the edge types. That tells us that E is a back edge. We just proved 10 minutes ago that a graph has a cycle if and only if it has a back edge. So E is a back edge, then G has a cycle. And there's remember we assumed that we started with G does not have a cycle, then we did a proof by contradiction. So we assumed there's this edge going from right to left. That gives us now the contradiction. Oh, if that happens, then there has to be a cycle. So if there is no cycle, then we could not have had this edge going from right to left. Questions? Yeah. Okay, that's a good question. If you order the vertices increasing, then you then this would be the opposite, right? This would be that post U is bigger than post V. So we would go back here So where does U finish after V? It could be here, it could be a cross edge, or it could be a tree or forward edge. So then that wouldn't give us anything in the proof. And in fact, you could probably construct an example where if you do that ordering, you will not get a valid linearization. So like if you do the ordering you're suggesting, which is the other way around, you would get a wrong, you would get an ordering which will have an edge from right to left, even though the graph doesn't have a cycle. Other questions? How many are more roughly clear about the second part of the proof? Half-ish. Still about half not clear, so questions? We have time. Yeah. Well, you mean this graph? Well, the way, okay, yeah, so this graph doesn't have a cycle. So this ordering doesn't have any edge from right to left. This is a proof by contradiction. So it's saying that if you throw in, if you had some back edge, so we can do this actually. So what if you had some back edge from E to A? What if that existed? The proof says then E would be a back edge. This edge E would be a back edge in the DFS tree. We can check the DFS tree. So what was E? That was the edge from E to A. So E to A, if we had it here, oops. Let me copy this. So if we had the edge from E to A, you could see it's a back edge. So if you want to think about this proof mapped onto an example, this is the right way to do it. To imagine if there was an edge violating this order, that it would be a back edge in the graph. Other questions? Yeah. Say it again. How do you tell? Like how to construct the ordering? I mean, so DFS, let me actually give the algorithm and hopefully that answers your question. So so inside this proof, we're buried an algorithm essentially to construct the linearization. This gives an algorithm to construct a linearization. Well, to construct, let's just say, a linear ordering of a DAG. And let me spell it out for you. So 1, run depth first search on G. Then 2, for all edges E equals to from U to V. No, so second step is sort the edges of G according post number. And then output sorted order. That's it. The time is the time for DFS, n plus m. This is DFS. Plus the time for the sort. So sort n log n, but here we're sorting the edges, so it's m log m. This is the sort. And that's just theta n plus, oh, excuse me, we're not sorting the edges, we're sorting the vertices. We're sorting the vertices according to the post number. So this is not m log m, this is n log n. And so this n log n dominates the n term, and we get n log n plus m total time. N log n plus m total time. The post numbers, again, are just written, they're written by the, that's part of the output of the DFS, is just to write the finish times. And so we learned this algorithm here to construct the linear ordering. We also learned another algorithm in the beginning, which we didn't explicitly give, but this algorithm to find if G has a cycle. Right, so I'll write this explicitly. So this gives an algorithm to determine if G is a DAG. And the algorithm is just one run DFS on G. Two, for every edge, we just check if there's a back edge. So that's all we do. For every edge E equals UV in G, if, so remember back edge definition, U's interval is contained in V's interval. So if the interval pre-U, so pre-U post U is contained in pre-V post V, then output, we found a back edge, so we output cycle found and then exit. Otherwise, so we do an end if. Create a little more room here. And if and for. And now we just, if we got to this point, we output no cycle. Four, 5, 6, 7, 8, 9. This is our algorithm for finding if a graph is a DAG or not. And this algorithm, runtime, so DFS DFS is the usual theta n plus m. And the rest, this is just a loop that takes m time. And in here, we're just doing constant work. We're just comparing 4 numbers. So the running time is dominated then just by the DFS. Final questions? Okay, so I'll stop here.